It's really an incredible pleasure for me to welcome our keynote speaker, Dr. Rose Picard from MIT. She has an incredibly impressive resume, and I will not go through all of it. I just wanted to give you one or two highlights and then save the time for her. She's an American scholar and inventor. She's a professor of media arts and sciences at MIT. And she's also a founder and director of the Effective Computing Research Group at the Media Lab. She's, in addition, a co-founder of the two startup companies, at least two, Effectiva and Impatica. In 2019, she was elected the National Academy of Engineering for her contributions in effective computing and wearable computing. In 2021, so last year, she was elected to the National Academy of Inventors. What is the National Academy of Inventors? It's an institute that recognizes outstanding inventions that have made a tangible impact on quality of life, economic development, and the welfare of society. If I think about MIT as an institution, and if I had to think about 3 or 5 or 6 people that to me define the soul of that institution, one of the 3 or 4 people I would think about is Dr. Rose Picard. She's truly a pioneer in this field, and she's one of my heroes. So please welcome Dr. Rose Picard.
Thank you, JP. That was super sweet, very touching. Yay, we're good. As I told JP earlier, I'm excited to be here, and I'm going to hopefully be here all day is my plan, because there's so many of my heroes here in the audience doing super cool work, so I'm really thrilled to be here with all of you today. I'm going to talk about, sorry, a little bit of a depressing topic, but hopefully you'll think some of the work is interesting and hopeful as well. First, disclosures. In addition to being a co-founder and shareholder of Impatica and Effectiva, that is now owned by Smart Eye AB, Effectiva is not Impatica, I also have Stern Strategy, Apple, Samsung, Harman, and an online course on innovation with wearables and digital health. All right, probably you know the bad news. Not only since a couple years after the Apple phone came out, and of course we can't blame it on that causality. Lots of things are happening in the world, growth of YouTube, changes in social interaction, sleep decreasing, lots of stuff. Depression has been going up, especially for our youth. Here, the work of Twenge and all people, especially under age 26, have shown a slope up, whilst older people had kind of stayed steady until the pandemic hit, when globally numbers have gone up. And in this study published in Lancet, the argument is that depression prevalence actually tripled during the pandemic. And the bar graph on the right is adults 18 and up, not exactly comparable here, but the biggest impact is on the youngest group. I'll include under 40 in that group now. And probably all of you, I know, I'm just curious, how many of you have a friend, family member, colleague, somebody you know who's struggled with depression over the last couple of years? All right, it looks like 100% of the hands. So it's a bad problem, and it got a lot worse recently. Now, you know, first thing you do when you bring up AI, smartphones, wearables in this space, people say, come on, you guys are part of the problem, right? Well, I think a lot of what we've engendered for behaviors may indeed be part of the problem. And in fact, there's nice causal studies like out of UPenn showing that cutting social media use to 10 minutes a day actually does improve several well-being variables. So it's not just correlation at work in this space, although there are a lot of correlation studies also. But it does appear that we can make things worse. But of course, we don't want to make things worse. We want to figure out how to make things better. So today I'm going to talk through, most of my talk is going to be on this first item, so don't panic when half the time's gone and we haven't gone to item 2 here. I'm going to focus on some work we've been doing, also especially with Simon Fader, who's right here in my lab. You can raise your hand because Simon can also help answer a lot more detail than I'll have time for in this talk, on this study that started with a grand challenge study with MGH and now has expanded to an NIH-funded trial with them as well. monitoring depression. Then I'm going to spend a little bit of time after that on some things we're working on, how technology might be able to help sooner. How can we actually make digital therapeutics something people want to use? And then a little bit of the concerns about this technology, as well as some hopes. All right, this study, and I'll put up a slide of all the collaborators at the end, is one where we set out to see if using wearable and smartphone data, we could collect passive information that could characterize somebody's depression level. And you're all familiar with this. In fact, Giorgio showed also microbiome in there. I wish we had microbiome data, but we have instead a whole bunch of other things related to your 24-hour activities here that I'll go through in a little more detail. We've got, for example, regular surveys on the smartphone. We've got occasional measurements of EEG during sleep, periods of 4 nights, taken twice. Physiological measures here using the Impatica E4, and on both wrists, which I know is a bit odd. I'll explain more about that in a moment. Some vocal characteristics, and also we did not measure the content of what you're typing on the phone, but we do measure your social interaction with others on the phone. In this protocol that lasts 8 weeks, we have the continuous wearable data, including electrodermal activity, pulse rate and pulse rate variability, temperature and 3-axis accelerometer, and continuous mobile phone activity. We have daily surveys about your mood, your sleep, your behavior. Every 2 weeks, they're getting gold standard assessment of depression from our partners at Mass General Hospital. And we have some weekly voice tasks, and then the in-home EEG sleep measurement, 4 nights in the beginning, in the middle, and at the end of this 8-week period. So to summarize, the data is E4 data, the smartphone data, some of the vocal audio diaries, and some of this EEG data. And compliance is pretty good, actually, here, I think, given wearing 2 big devices is kind of clunky, and these people are diagnosed with major depressive disorder. Diaries was the lowest compliance here, but still quite good. We generated over 800 features, about half from the phone and about half from the wearable. A unique thing about our features is that they are chunked by time of day, and that becomes especially meaningful to have that context for some of the kinds of analysis we do. So for example, a signal like electrodermal activity on the wrist has very different characteristics during sleep than it does during afternoon study sessions. And it's important to know that context. In fact, that's a general statement in all of this work. The more we can understand the context, the better we can interpret the wearable and smartphone data. I mentioned this oddness in our study of including 2-sided electrodermal activity, 2 E4s. Obviously, 2-sided heart rate doesn't, should tell you the same thing, maybe just cleaning up the noise a bit. But 2-sided EDA, we think now should, in some cases, be different, although in most cases it should look the same. This comes from Detour. I've had the privilege of taking in my work, learning a whole lot from epileptologists and neurologists about different neural patterns in the brain. And in some cases, patients consent for serious medical reasons to having a craniotomy where they let you open the skull and go in and directly electrically stimulate the right amygdala, the left amygdala, the right anterior posterior hippocampus and cingulate, and the left one. And when they do that, for example, when they stimulate the right amygdala, you get a large right palmar skin conductance response, shown here in red, and very little on the left. Whereas when you stimulate the left amygdala, you get a large left skin conductance palmar response and very little on the right. So there is an ipsilaterality, same-sided response in these regions of the brain. There are other regions of the brain that, when stimulated, cause contralateral or bilateral responses. So it's not so simple what's going on. But when you're looking for distinguishing a subtype of depression that might be anxious depression or fear or phobias that might involve more of what would be typically imaged in an MRI as more right amygdala activity in a strong right-hander, then it's interesting to look at this sidedness. So we see in real life that the same person can usually have the same thing. Here, what you're seeing is skin conductance in the top graph. Red is on the right wrist, in this case, blue is on the left wrist. Underneath is the left wrist activity, the right wrist activity, and both wrists temperature. Activity and temperature may not differ much, but the electrodermal activity can change a lot, in particular, we think, with like a social threat type situation. So if somebody's living a lot more like that in their life, that may help us digitally phenotype a depression. What we did is we collected this raw passive data and these gold standard Hamilton Depression Rating Scale score labels every 2 weeks. We've collected more than this, but this is what's going to be used in the results I'll show you in a moment here. This is pre-processed in lots of different ways, in particular looking at different time chunks and cleaning up the data. And then we model it lots of different ways, much more than what I'm showing you here today. But just so you know, there's different machine learning methods, different ways of looking at the features, different kinds of models for putting that together. And then what we are comparing on is the mean absolute error of the estimated Hamilton Depression Rating Scale score. These first results that we published here are showing on the vertical axis the predicted value of the Hamilton Depression Rating Scale score from the algorithm. Higher is more depressed. And this is almost entirely passive data. There's one piece of data that involves the first visit with the psychiatrist, which is important. If we throw that out, the results are not as good. Getting the psychiatrist, first of all, to characterize the person well and get a strong screening baseline is helpful in the results I show you. The rest of the points after visit 1 are entirely generated by passive data, the smartphone and wearable, not including the self-report data from them about their feelings. So just passive monitoring. The horizontal axis is the Hamilton Depression Rating Scale score given by the expert psychiatrist. So we see in the beginning really great results, but if you scrutinize really carefully, you'll see people kind of clustering around themselves, right? So there's not huge variability in this set. We are in the middle of a larger NIH-funded trial to get, and with some adjustments to the study design, to get more variability within person. Now, the results I'll show you are evaluated in 3 different ways. First is probably not really useful clinically, but it's what machine learning people default do, right? We take the data, we randomize, and we randomly draw a training set, and we randomly draw a test set. There's the risk that you're drawing some from the same person, right? Which could make your results look better than they should or have other correlations in that data. So we also do 2 other ways. This one still knows something about a patient's past, but we split in time. We separate their past data for training. We use their future data for testing. That would be a reasonable clinical scenario where you might learn a little bit about somebody and then you try to track their future data changes. And then the hardest scenario is we have no data on the new patient. We just use data from existing patients to try to predict what might be happening with a new patient. So 3 scenarios: random, time, user. When we compare different methods with these random, time, and user split ways of training and testing, we see that linear regression is not very impressive. The machine learning methods all beat the linear regression, and pretty consistently random forests do pretty well here, and we can talk more about a lot of other things we've tried since then too that aren't shown here. But very humbly, when we look at the personal average, like suppose you just knew somebody's average HDRS or median HDRS, if you knew it for the group median, the group mean, the personal first visit, the personal median HDRS, the personal mean HDRS, these beat the machine learning. So at first you might say, well, the machine learning's worthless, this is really depressing. Gee, Roz, great. Well, if we think about it, it's still kind of cool, right? That even if you don't know those things, the passive data plus one visit is actually tracking this pretty well. But it is still a small set and not a lot of variability. But we want to do better. And so we've looked at lots of ways to personalize models. One of the ways that is working best right now, but we still need a lot more data, and this is work led by Rob Lewis in my lab, is to use mixed effects random forests on the data. When we do that, the random split, we beat the personal baselines and group baselines. We also beat it for the time split. Remember, that's when you can train on some past data of somebody and test on their future data. User split, we're not beating the personal screen, but remember that's like them coming in and having an expert tell you what they're doing, and these are people without a lot of variation. So there's really not adequate personalization in that. I've just said that. Just for those who aren't familiar with this method, this is not a method we created, although I wish we had. It's a pre-published method here is the reference. And the essential idea is like with linear mixed effects, instead of this fixed effect term trying to gather information across everybody in a linear way, we replace that with nonlinear machine learning, in this case, a random forest. And then the random effects are used per individual to get a bit of that personalization. These improvements, when we measure the lift per person, they are statistically significant. This lift is the reduction in error over each person's individual baseline and their MRF forecast. And that is statistically significant. We need to do a lot more. Like all of you, I think we want a lot more data, and we want to analyze this not just for Hamilton, because that's just one measure and it's far from perfect. There are lots of other ones, none of which are perfect. So we have lots of ideas how to extend this. And I'd say the biggest one we're focused on right now is getting more heterogeneity and getting more numbers of these heterogeneous patients. We also are very interested in characterizing the network dynamics, what's going on, and understanding, it's interesting, we have movelets for dynamics we're used to seeing. These would be, trying to understand more the dynamic elements that are contributing to us doing better or worse. And here is the list of amazing collaborators and supporters on this first project. Paula Pedrelli has been heading the effort from the MGH side. Simon's been really heading all the nuts and bolts of what's going on our side here. All right, that's one example of the smartphone wearable data passively estimating and with the MRF beating the personal baseline when you have a little bit of prior data for somebody and using it to test on their future data, and also in the random scenario. What we'd like to do, though, is not just monitor how people are doing, although that's useful, but we'd like to be able to help us actually feel better, right? Help our friends feel better. This is my one graph that's not real data, warn you, dangerous at a data analysis conference, but that you can appreciate that there are thousands of things rolled up into this vertical axis. So this is a concept diagram. Imagine that you are doing well. And and this is time here, high is doing well. You go into a new job or university where it's awesome and you're doing even better, nice bump up, but then major stressors hit, which is normal even before the pandemic, right? And you take a little bit of a dip. And then some people keep going down from there. They are fragile. And some people bounce back. They are resilient. These people can look exactly the same until the major stressor hits, or at least they do with a lot of these variables, or do they? Are there things we could see earlier if we measure enough stuff to start to understand these differences? So we are looking to see what those things are and how we might intervene while you're especially if you're on the red line, not the MBTA in Boston, but the red line and going downhill, right? So if you could monitor very subtly below our usual just noticeable difference, but if the smartphones and wearables could sense that you're kind of on that downward trend, just like Giorgio showing that upward resting heart rate trend, then maybe even when you're not aware that something's bad, we could intervene. This is the motivation for our original study with New England college students, where we monitored not only wearable and smartphone data, but also dim light melatonin in partnership with Brigham and Women's Hospital here at Chuck Seisler, Beth Klerman Sleep Clinic. We monitored sleep data, physical activity, light exposure, autonomic stress with the wearable, texting and phone call behavior. We recruited people with a social network, and we monitored GPS coordinates. This was all before the pandemic. And it's interesting because the insights were things like people did better if they got out and about. People did better if they interacted more with people socially. And then when the pandemic shut that down, all of us were like, oh no, this is not going to be good. So this study has the most tortuous acronym I've ever seen my students give anything. Sleep networks, affect, performance, stress, and health using objective techniques, or the 30-day snapshot study. We started by trying to separate out mood, health, and stress as different tasks, thinking multitasking machine learning would give us really great results, leveraging, taking out the mood prediction stuff that was related to you being sick or just being stressed, right? So if we would jointly train neural nets on that, in this case deep learning, we thought that it would improve the performance on each of them. It turned out that did not work very well. Here's a comparison of trying to estimate tomorrow's self-reported mood, which was reported every morning and evening by the students, tomorrow's self-reported stress, and tomorrow's self-reported health, healthy, sick, on a 0 to 100 scale for each of these variables. The single task learning accuracy is shown here for 3 different models, a logistic regression and support vector machine and neural net based. Multitasking is shown in the middle for each of these, which is where we're training separately but jointly models on the stress, the mood, and the health. And the best of all was when we multitasked on people. So similar to the MRF model, the mixed effects random forest, if you actually treat each person as a task, that gave significantly better results. In fact, we've now found this in other studies we've done on pain and other digital health topics too, that treating a person as a task in these multitasking models gives a significant boost. So it's a kind of personalization that seems to be very effective. Side story, the fact that it did so well on health when we were really throwing that in as a controller for confounds on mood and stress actually led to a whole side set of projects very similar to Giorgio's work, where we wound up going off and forecasting also with Duke and Columbia and Michigan, some joint work on forecasting initially H1N1 and rhinovirus, and then later also SARS-CoV-2. This, but back to the mood, stress, and health, multitasking with people. There's some early results shown here that were the best. The most important thing about this slide is we open sourced all this code. So if you want to get started using some of these methods that we found were really useful, we're just giving them out for free. And we hope you'll not reinvent the wheel, but hopefully help us make it better still. All right, how can we change our forecast for tomorrow? Let's say it says tomorrow your stress is going to be worse, your mood is going to be worse, and your health is going to be worse. That's pretty depressing. I don't know about you. A lot of people won't want that app, but they will want the one maybe that tells them what to do to make it better. We don't have that yet. What we have is a partial step toward collecting more evidence-based understanding of things that in a context with this restricted set of data of college students are associated with feeling better. I do not have causal results on this. However, we think this is still better than just the generic recommendations that are often out there. So this is the work of Ehi Nosakari, now Dr. Ehi Nosakari in my lab. who used latent Dirichlet analysis, and instead of trying to optimize the prediction of tomorrow's mood, stress, and health, which we've already worked on in other ways, she tried to figure out which variables that you can actually control in your life. If you build a model using only those, which of course is not going to be the best model, but you try to build the best model you can using only those variables you can control. What does that tell you about which variables get weighted highest for affecting tomorrow's forecast? And sorry, they're really small, but the ones that are circled here, the goal is to build the model that predicts if tomorrow you're going to say you're calm or you're stressed. And again, 0 to 100, here a lasso regression is showing the weights of the coefficients. And what we see is that the rightmost one that was most associated with being stressed the next day is the variable of having low sleep regularity. We found separately in careful analyses that when we even controlled for duration, the people who had very irregular bedtimes and wake times, if you just looked at their sleep-wake patterns from day to day and how correlated they are with each other, our sleep regularity index, that having a low correlation index of sleep also means a high lasso coefficient related to more stress the next day. The duration of sleep, the bedtime being regular between midnight and 1 a.m. Are over on the left associated with calm. The biggest thing is positive social interaction is associated with calm the next day. Again, this was before pandemic, which made us really worried during pandemic because that was changing. And those of you who have had to move things to Zoom, or if you've only met people on Zoom, I don't know about you, but in my experience, relationships are, it's just harder to have those positive social interactions online. Sometimes things that are neutral seem a little more negative online. I think the negative ones happen a little more easily or get misconstrued as negative even when they're neutral online. So these may be important elements to watch. All right, finally, how do we make digital therapeutics more engaging, and a few more hopes and concerns? With the genius of Craig Ferguson and Sarah Taylor and others in my group who've been collaborating to make digital therapeutics fun, we have built some games, and we're giving these out for free, and we're not even selling ads or anything or taking your data. So please feel free to try it yourself. Give us your feedback. The idea arose originally when a large pharma company, Takeda, said, these kids, we need them to fill out these daily surveys. They don't do it. We need them to fill out more than 90% of the days. It's unpleasant information they're having to report. How do we get their compliance up, right? They use paper surveys, which have less than 20% of people filling them out for the goal of more than 90% of the days. And we replicated that. We didn't want to compare against paper, our game, so we built a digital epro, right, so that it would remind you and prompt you. So we have something a little bit more state-of-the-art on the phone. That alone does a lot better than paper, no surprise, especially with kids. And then here was the first results of the first game we ever built, beating significantly the epro and the paper. What did we do then after getting people to fill out forms? We said, gee, there's a therapy for depression that is evidence-based when administered by psychiatrists. Could we put elements of that into a game? And this therapy that we chose is behavioral activation. The basic idea is when you're depressed, you don't do things that make you feel better, so it's this bad cycle. If somebody gets you motivated or something gets you motivated, you might go and do some meaningful activity, which might make you feel better, which might make you feel like doing another meaningful activity, and you get in the virtuous cycle. This is one of the elements of behavioral activation. Another key element is reflecting on it, and those are the two key elements that we put into our game. When people were prompted with this, which you're all encouraged to try out or share with your friends who may be struggling, and prompted people for how they did the activity, most people said they felt better afterwards. So that's an important piece of feedback. But what about engagement? Did we make it fun? This paper by Baumel et al. In JMIR surveyed digital mental health interventions that are out there already. I think they had to have at least more than 1,000, 10,000, I forget, downloads, successful ones that are out there. And by day 30, 3.3% of people are still using them. How did we compare to that? First, we also want to look at mobile games that are not intended to be therapeutic, just things people play for fun, crosswords, fun games, Angry Bird, whatever. And those do much better on day 1, but by day 28, they're still barely double the digital mental health interventions. How's our first attempt at putting behavioral activation, a digital mental health intervention, out there? Well, we more than doubled the other mental health apps, and we're currently in the top 15% of mobile games in terms of engagement. I don't know about you, I think there's still a lot of room for improvement here, right? But it's exciting to see that we can put a therapy in there and have it land in the top of the mobile games. So here's the info. I'll encourage you to download that and get back to us. We're partnering with other people. We've got a full platform where we can make modifications, measure data, see what's appealing to people, customize for different groups. And we're in a study right now with MGH, with pregnant women, that is looking amazing. The engagement rates shot up even double high again, really astonishing, very exciting to see. So we think there's a lot of room for customization and improvement there. The Fast Company recognized this with their Wellness Innovation Prize last year. All right, finally, a few concerns. The hope is that we could be much more thoughtful about how AI technology, smartphones and all, are designed in the future, recognizing humbly how they have probably contributed to a lot of the detachment and loneliness and problems out there, and rethinking everything we design to try to bring people together with social interaction, not trying to design people out, but trying to design people in. Hopefully you've gotten a sense from at least a little bit of the data shown that the passive and AI analysis of this passive data actually is informative for mood, stress, and health. With the psychiatrist's initial assessment, very important, we haven't engineered out the psychiatrists. We can, with personalized machine learning, training on some past data, testing on some future data, get very accurate personalized estimates of Hamilton Depression Rating Scale scores. We hope with more data, we might be able to do better digital phenotyping of different types of psychiatric conditions, especially with better dynamic characterization, and enable more effective personalized treatments instead of today where they start down a list of favorite medications and just kind of cross them off depending on side effects. That needs to go the way of the dinosaurs. We really need to learn patterns and associate those with treatments that work so that people can get matched right away with something that is more effective for them. There's a lot of ethical things we could talk about. I picked 2 to bring up. One is that we're always asked to share our data and de-identify it. Well, you may know some of our work that Javier Hernandez led in our lab, where even your smartphone, if it's in your pocket right now and you're holding still, the accelerometers can sense your heart rate and respiration. And furthermore, the signature of your heart rate and respiration in the accelerometer, okay, not in a PPG or an ECG or a chest band, but just in the accelerometer pattern, has been used to identify people. All right, so just de-identified accelerometer data, right, can be used to identify people under the right context. So we talk about not just de-identified, but re-identifying, and restricting people from re-identifying data. The second one is that I don't know how many of you are watching what's happening in the EU, where they've proposed regulations on AI to prohibit employers from monitoring health data and affective data at all. And in some cases where they might be allowed to do it, it needs to be explainable. If it makes a decision, if it contributes to something like a Hamilton Depression Rating Scale score, you need to explain how it got it. And decision trees, maybe are easy solution for that. But a lot of the fancy methods we're developing may not give satisfactory explanations to the physician. So we do need to be thinking a lot more together, not just about getting accurate estimates and estimates on the things we can change to actually make tomorrow better, but also estimates that we can explain so that we can build trust, truly be trustworthy, as well as explainable. All right, I've gone through a whole bunch of things here, a little bit about our grand challenge study. We do have a big ongoing study in that space, a little bit about trying to help sooner, big need there for better data sets, bigger data sets, and causal inference, not just the associations we've shown. I think we need a lot more work together on helping make things more engaging. And we also need to work together as a community to, I think, not engineer out the people, but make sure people are coming together in this technology. I think the people in this room today, this amazing group here, I'm looking at the brilliance that really could make all of this come together, not just with the wearables, the smartphones, the AI, all of the things you bring, but I think people who care about people, and we can come together and try to make that a much better future for everyone. So thank you.
Thank you so much.
Hi, so thank you for the talk. It's very impressive. So for a couple of the projects, when you collect the multimedia data for the patient and trying to do prediction, what's your principle? What's your idea to combine this information together?
There are a lot of ideas for how to combine multiple modalities, and I think a key thing you want to do before you just slap them all into a giant feature vector, because the dimensionality is crazy. I mean, I don't think anybody here is as old as me back when I used to teach the curse of dimensionality in the first machine learning class at MIT. But I would be horrified, right? I still am, by the dimensionality of the features. So I don't think just throwing them all into a feature vector, although that's kind of become the way people are doing it, is the best long-term. Also for explainability, I think it's going to hurt us. We think that doing a sort of a mix of the feature engineering, and maybe we have to iterate back and forth between the feature engineering and the stuff them all into an LSTM kind of approaches. But I think feature engineering at the level of where you're associating features with contexts and you're associating them with things people can change may be very important for explainability, understandability. Again, it may not optimize the MAE, the error, but we need to think about multiple ways of doing this. And that happens right up front when you're combining the features. Also, we need to recognize that there will be dropout in some channels sometimes. So methods that work by putting them all together can be very brittle. So sometimes methods that learn which ones co-occur in interesting ways and work on that up front can be better. So I'm a big fan of still doing a lot more not just feature engineering, but feature understanding of what's actually relevant and trying to reduce the dimensionality. In the back?
Thank you very much for this. This is fascinating. Regarding features, could you talk a little bit about features that are maybe cutting edge that you are interested in exploring? So, for example, we have calendar data now. We have data on the social media apps. So I'm curious, what types of features might be interesting for you to explore in the future, and then on the flip side, also, what types of interventions are you interested in exploring, like mindfulness-based stress reduction, for example, has been peer-reviewed. So interested on both sides of those cutting edge areas.
I teach a class on AI and mental health now. We're going to go through the long answer to this. There are, the first question, the second one was the other interventions. The first one was the features. Yeah, other features. Golly. Just about anything reflects affective information, just about anything people do. But different ones have different trade-offs with privacy. If you're in the automobile, in the beginning, people were not comfortable with a camera pointed at them. Now it's there and I don't hear them complaining. They're quite comfortable with the steering wheel sensing that they're gripping it stronger, right? That today was a more stressful commute. But they may not be comfortable with their boss. In fact, in general, they're not comfortable with their boss sensing just about anything, right? So I think we have to think not just about what features, but what contexts. And we've absolutely got to show respect for people's feelings throughout this. So just willy-nilly saying, I'm going to get all your data, I think people should be increasingly worried about that, especially now that we see large healthcare companies giving their data to people like Google researchers, when I don't think the patients originally had that in mind, right? So we need to be I think, a lot more thoughtful about people's feelings and what could go wrong, what harms could come to them with some of the modalities. That said, any modality that we could feel would not create harm is potentially interesting. We're doing a lot more work in our lab with sentiment analysis, with speech. I didn't talk about the speech data here. I'd say the adverbs of just about anything you do can reflect your depressive state, your energy level, your health. So it's more a matter of what you're comfortable with. But I can tell you some of the things people have proposed, like somebody came in the other day with cameras in the workplace monitoring people's gait and emotions that way. And I was like, not in the workplace. So sometimes it's not the modality, but it's where you're doing it and how it might be used. Yes.
So in neurological drug discovery, we have a high record of failure in clinical trials. And part of that might be accounted for by the fact that we are sampling patients weeks apart using the traditional scales. So tools like ecological momentary analysis to get more sampling are upcoming, but they're still not really looked at by regulatory agencies as a place where they're going to really help characterize the disease. So what do you think about your tools as a way to get better sampling and resolution to what the disease process is on an hour by hour or even day by day basis?
Mm-hmm. Here, I'm going to remind people that I wear two hats. I wear an Impatica consulting and research chief scientist part-time hat and an MIT hat. On the MIT side, we're less concerned about that. But on the Impatica side, they actually sell not only devices like Embrace Plus that I'm wearing, but also services with digital biomarkers and a whole platform that's got a giant slide of regulatory things that's satisfied. I won't go through all of them. Several FDA certifications and other EU and US pharma people dropping in with audits and making sure that everything is done well on the back end as well as what you see on the front end. So there is a lot. I would say that's actually now. I think it is the future, but it's quite active now. It's in a lot of clinical trials right now, giving data at different sampling rates, because you can customize what you need for each trial, which sensors you want and which sampling rates. And we give all the raw data. If you want, it can also be processed according to methods that can be transparent about. So that is present. Experience sampling with self-report and with physiology and behavior, as we saw with the nice activity work earlier that was shown. And also with speech and behavior and interactions and social, all of that now is available. However, regulations are rising and saying, don't take my data, right? So it's all the more important, I think, that we get ahead of that and talk about how to respect people and the potential harms, so we prevent those harms. Otherwise, there could be a huge backlash, and a lot of this stuff really could be shut down, and I think everybody here would agree that could be bad for the future of health if that happened. You keep an eye on time for me here, because I didn't notice when we actually started. Over here, Jesse.
This was fantastic, thank you. I have a question for you. So you're developing mostly machine learning, which means that you have an outcome that you're trying to predict. And so how do you handle the idea when that outcome might not be such a good gold standard? So maybe you think that your tool actually outperforms the gold standard, but therefore they don't match.
Yeah, definitely. And HTRS, while it's the gold standard at Mass General Hospital, ranked #1 in psychiatry, as soon as you go away from MGH, somebody else will tell you it's a bad standard, and there's other ones they say are better. So we usually let our clinical partners pick the standard, but my preference is to measure multiple things. On the first slide, I think I showed you there are a bunch of things we're measuring. We've done some analysis with those. Simon, wherever he just went, could fill you in a little bit more on that. I think if it's brittle to that measure, it says we're not really capturing it. And if we have like two measures that are supposed to capture the same thing and we get a significantly different performance on them, that worries me, right? Maybe we're overfitting to something particular to one of those. So I actually kind of like when we have multiple gold standards, if you will, and we can try to tease apart what's robust to this versus what's picking off some special aspect of one of them. Definitely room for improvement of those gold standards. Yes, Temi.
Thank you so much for the talk. I just have one question in terms of this data can be used to re-identify.
Yeah.
I'm interested in what are some of your thoughts in how to move this forward, because currently there's many people collect their own data and help models on it, but they don't really test it on other data, and then there's a lot of new researchers and a lot of work that would progress if there were more open data. So kind of this
Yeah.
there's a balance, but what is
There is, and I would not be comfortable sticking our data on the internet. It's funny, in the early days when I was really just a computer vision person, we did that all the time, right? Just put our data out. Now, given what's on the internet, you really kind of need to share data with people you trust who are respected research. So NIH is now, they've set up this data repository. If you get NIH funding, you have to put your data there. They will say only put de-identified data there, to which, we should all say, we can't guarantee this is, we de-identify by HIPAA, but look, you can re-identify this. So what we really do is we require people to sign something if they're using it, that they're using it only under IRB. They promise not to re-identify, because certainly you can triangulate and use de-identified data to re-identify people. So not fully open on the internet, but open to communities that have to jump through hoops. Time for one more in the back? Okay, all right.
Thank you for sharing your fascinating results of these studies. I was wondering, given the fact that people interact less and less, or participants of studies interact less and less with digital tools, I was wondering whether it was the same with using less wearables during the studies, leading to missing data, and whether there was a missing data, how would you encourage participants to engage more and more with wearables, or whether there are statistical things that help you to account for that?
Yeah, this is a great question for Simon. He's doing lots of analysis. Like what does it mean when the data is missing, right? Is the person sick? Is the person traveling and they lost contact with Wi-Fi or they forgot to take their charger? So we have been looking into all the different reasons it's missing, from, sensor breaking to person losing Wi-Fi and upload access or whatever, or phone lost. I think we do need to think carefully more about the missing data. When there's a channel dropout, whether it's discomfort with what's being sensed, go back to, honoring people's feelings with this. Maybe they're uncomfortable with something. And we need to get to know the participants a bit more to look at those. If they're just wearing a device like this in the study, what's the bias? What about the people who aren't wearing one? Is it just cost or not knowing about it, or is it something else? And we have seen some systematic biases in our missing data, and it's very important to try to understand this. Yeah, great question. All right, thank you.
Thank you so much.